In this video, we want to determine convergence or divergence of a series using both comparison tests. So we have here the series sum from n equals 1 to infinity of cosine squared of n over n squared. We want to determine if this converges or diverges. So my intuition behind this is because I see the n squared on the bottom and something that is bounded on top, like that's no bigger than 1, this should be a convergent series. 1 over n squared converges by p series, and so we know this should be a convergent series. Now I have to figure out how to justify it using both the direct and limit comparison tests. You only need to do one of these, but I want to showcase both to show you how that would work. So for the direct comparison test, we know that cosine squared of n is always less equal 1 for all n. That's because cosine is bound between -1 and 1, so when I square that, that also stays between -1 and 1. This means that cosine squared of n over n squared is less equal 1 over n squared for all n. And I know that the sum of these guys is a convergent series. So our argument is then, because this is true for all n, and sum n from 1 to infinity of 1 over n squared converges, we know that our particular series cosine squared of n over n squared also converges. Because both series here has all positive terms, the cosine squared of n makes sure it's always positive. And so if a bigger series converges, then our series must also converge by the direct comparison test. Now, for limit comparison, we'll be a little more creative in how we set this up. And the reason for that is because of the format of this series. So your gut reaction might be, let's compare to 1 over n squared, because that converges, and we know that converges. But if I look at the limit as n goes to infinity of the ratio, an over bn, where an is my series, I get the limit as n goes to infinity of cosine squared of n over n squared divided by 1 over n squared, which is limit n goes to infinity of cosine squared of n, which does not exist. And our limit comparison test requires this limit to exist and be a number between 0 and infinity to know what happens here. So we can't use this approach to see what happens. What can we do instead? Well, let's try a slightly smaller power of n in the denominator. So let's try comparing to bn is 1 over n to the 3/2. This series also converges because the power is bigger than 1. But now when I do my limit of the ratio, I get cosine squared of n over n squared divided by 1 over n to the 3/2. When I cancel out these powers, I will end up with a square root of n in the denominator. This is the limit as n goes to infinity cosine squared of n over square root of n. And by the squeeze theorem, this limit equals 0. The top is bounded, the bottom goes to infinity, so the ratio there is going to go to 0 as n goes to infinity. So now we're in one of these sort of side cases of limit comparison, where if I have that this limit equals 0 and the bottom series converges, the top one also converges. So for this choice of bn, we have that sum n from 1 to infinity of bn converges, and limit as n goes to infinity of the ratio an to bn is 0. So therefore we know that our series, the an series, must also converge. This was a little bit trickier just because of the cosine squared over n bit that does not exist in a limit. So to be a little more careful how you set this up to get to an actual thing that will work using a limit comparison test. Basic idea of this idea was that if I sort of give myself some wiggle room on the powers here by going down to a 3/2, I have all the way up to an n squared that I could use to get something reasonable. But if I give myself some wiggle room here, go to the 3/2, I then have this extra square root of n down here to cancel this out. The problem you'll see with something like this is if this was just an n, not an n squared, then none of our tests work to determine if that series actually converges or diverges. Nothing you can do is going to argue that it's actually going to converge or diverge. But in this case, for the n squared, you can get either direct comparison or limit comparison test to tell you that this series will converge. Not find the value, because that's really hard and we can't do that. We can at least know that it's going to converge to something.